Hello everyone, I'm Norman Wahlberger. Thanks for joining me on this adventure towards exploring dynamics on graphs and exceptional structures. Today we are going to meet some new exceptional structures of an algebraic kind as we make contact with group theory, introducing the Weyl groups for ADE graphs. So if X is an ADE graph, then W, or W of X, is the group of linear transformations of the populations on X, which is generated by the mutations S of X, as X ranges through the vertices of X. So this is in the context of linear algebra. So we're thinking of the populations on X as being sort of the integral analog of a vector space. It's actually officially a module over the integers, but think about it as a vector space where we're really just restricting ourselves to integer combinations. And we are looking at these mutations that we've defined as being transformations of this population space that are naturally linear. And they are typically invertible because S of X squared is the identity. And so that means that when we take products of these things, we stay within the invertible transformations family, and we generate what's called a group of transformations. And for the ADE graphs, we say this is the Weyl group of X. And for these graphs, these turn out to be finite groups. So we can actually do this for general graphs, and we'll later on talk about that. But that's much more complicated because for a general graph, these Weyl groups are unbounded. So it's hugely more complicated. So these are the simplest versions. And in fact, we'll see that the AN family is particularly simple and important because that's essentially getting us the symmetric groups. There are basically two important families of groups, that are sort of the fundamental examples. The symmetric groups on the one hand, and the general linear groups on the other hand. Okay, and these also have interesting connections with each other, and so we're going to be touching base with both aspects of this story. But at this stage here, I want you to think about the Weyl groups as being some kind of generalizations of the symmetric groups. So we do get the symmetric groups in the case of AN, but for the other ADE graphs, we're getting bigger or different or some kind of variance of the symmetric group. So have a look here at this little table here. Here's the size of the root populations on this side and the Weyl groups for the corresponding ADE graphs. So remember AD, there's the AN family, there's the DN family, there's E6, E7, E8. Here are the sizes of the root systems that we've talked about for those graphs. And over here we have the sizes of these Weyl groups that we are about to explore. So with the AN graphs, which is basically a symmetric group, we get an n plus 1 factorial. It's actually the symmetric group Sn plus 1. And these ones for the DN graphs are pretty close to these ones here, the sort of variants of the symmetric groups. And then for E6, E7, E8, we get some strange, remarkable groups. So for E6, the Weyl group has 51,840 elements. For E7, 2,903,040 elements. And for E8, always the biggest and the best, we get 696,729,600 elements in the Weyl group. So yes, there's much to say about these things, and still much remains to be discovered about these things. I mean, we're just sort of starting, really, in some sense, understanding these things. But in any case, I want to bring them into being today, okay, for us in a very explicit way, which is somewhat novel. So you're not going to find this presentation in most texts or papers on this subject. So I'm giving you a new window or entrance into this remarkable area of group theory. Okay, so what we're going to do is we're going to concentrate on the mutations, and we're going to start with indexing, okay, a labeling of the vertices For AN, we start from 1 to N, but for the other ones, we're going to start with 0. Okay, there's a 0 vertex in these other ones, and our labeling is going to start 0, and then 1, and then 2, all the way up to N. Okay, that's the order that we're going to use. We're going to use that order in order to create matrices. All right, so let's start by considering the adjacency matrices for these graphs. Okay, so this is relatively straightforward. Here's AN, for example. Here are the various adjacency matrices. They have sort of a common aspect. Note that I'm also considering, here's AN, for example. Here are the various adjacency matrices. They have sort of a common aspect. Note that I'm also considering A1, which is just a single vertex. It's sort of almost a trivial case, but it's not entirely trivial. So there the adjacency matrix is just the 1 by 1 0 matrix. And here's A2, where we just have 2 vertices, 3 vertices, 4 vertices. When we go to Dn, it's nice to do D4 a little bit separately. It has some special properties. So here is the adjacency for D4. Let's just check this just to make sure we're all on the same page with respect to adjacency matrices. All right. So we've labeled our vertices 0, 1, 2, 3. The vertex 0 is connected to 2. So that first column there, say, means 0 is not connected to vertex 0. It's not connected to vertex 1. It is connected to vertex 2, not connected to vertex 3. Okay, the next column, that's corresponding to the vertex 1, tells us it's only connected to vertex 2. Next column, associated to vertex 2, telling us that vertex is connected to vertex 0, 1, and 3. And finally, vertex 3 is connected only to vertex 2. And although I was going down the columns, we could equally go down across the rows because this is a symmetric matrix, as are all adjacency matrices for these kinds of graphs. Okay, and then if we looked at a slightly bigger D, for example, D5, then there's more of a tail on this side here, and then it looks much like this one, except that we sort of have to extend this ladder of ones going down here. So if we looked at higher Ds, there would be more ones going down here in a sort of predictable fashion. So it sort of looks like an AN on this side. It only up here is it sort of different from the AN family. Okay, then we have the EN graphs. So for E6, here it is there. That's the adjacency matrix. Please stare at it and convince yourself that that's what it looks like. And then for E7, there it is there. Maybe it's worth pointing out that since E6 is inside E7 in the obvious way, this adjacency matrix here is sort of found inside the E7 one. There it is there. And similarly, when we go to E8, there's one more vertex over here, and can we get both of them on there? Yes. So there's E8. The top corner of that there is the E7 adjacency matrix. You know, and for E8, for example, it's this vertex 3, which is perhaps the most interesting. That corresponds to this column right here. That's the one that has the most connectivity, as you can see with these 3 ones that are appearing there. Okay, great. So now we have the adjacency matrices. Now let's discuss the Weyl groups themselves. So we'll start with the AN graphs. Okay, so the A1 graph has only one vertex. How do we get the corresponding mutation matrix? It's very simple, but it's not entirely trivial. So what we have to do is we have to take the identity matrix, okay, which in this case is just a 1, and we have to replace that column with this column, so then we put a 0 here, and then we have to come back and augment the diagonal entry to get a -1 there. So that's S1 in this case here. And so then entirely the Weyl group itself, so I might just write that down. So the Weyl group here is then the Weyl group for A sub 1. What does that actually consist of? So it's a set, and it consists of 2 matrices. There's that one, and there's also the identity matrix. Okay, so I can also perhaps write it as maybe the identity, what's that, maybe E and S1. Okay, that will be another description of this group. So it has 2 elements. There's an identity element, and there's this single S1. Okay, A2 what do? We take the identity matrix. So this is another way of stating the procedure that I outlined in the last video. So in general, what we do is we take the identity matrix, in this case 1, 0, 0, 1. We replace the column that we're interested in this case the first column, with the corresponding column of the adjacency matrix. So the 1, 0 in the identity matrix is replaced with 0, 1. And then we have to augment or change that diagonal entry in that column to a -1. It's like adding -2 to the identity matrix part of it. So if we did the same thing for S2, then we would replace the second column of the identity matrix with the column 1, 0, and then we would have to adjust this element to give us a -1. And so we can check that these matrices really do capture the mutations that we're interested in, okay, by applying them to a population vector that encodes the population at the two vertices, say P1, P2. So if I define these two matrices, S1 like this and S2 like this, and then I evaluate this thing here, I get P2 minus P1, P2. So that is indeed the effect of mutation at the vertex 1 on this population. The P1 is replaced with minus P1, and then we have to add the neighbor. And similarly for this one here. Okay, great. Actually, because this is a very important case here, this A2, you might think it's rather modest because we're just starting out here, but actually this is already a very, very important example. And one has to understand this example really well. So I'm going to actually write out the Weyl group. So the Weyl group then is what? So what we have to do is we have to create products. We just look at all the matrices that we can create by taking products of these things. So we've defined S1 and S2. So suppose I take S1 times S2 and evaluate that. I get that matrix. That's a different one. If I take it in the other order, S2, S1, I get that one, which is a different one again. Of course, if I just take S1 squared, something like that, well, I'm going to get the identity matrix, okay, which is also in the group. How else could I get more? Well, I can just keep on, multiplying, right? I could take, after this, I could take S2, S1, and I could multiply by S2. Or I could take S1, S2, and multiply by S1. In fact, you see these two are the same, and that, of course, is no surprise because the braid relation tells us that when we have two adjacent vertices, then the corresponding mutations satisfy this property that S2, S1, S2 is equal to S1, S2, S1. And that's a general fact whenever you have adjacent vertices. Okay, are there any others? So these two are the same. Are there any others that we can get? So, for example, suppose that we take this one here and say we want to make something else. Well, if we added another S1 to that, you can see that that's not going to be anything new because the S1 times S1 that's appearing here is just the identity. So this is really the same as S1, S2, which is this one here. So that's nothing new. On the other hand, if we, say, did this one, instead of multiplying by S1, we multiplied by S2, well, what do we get? We get this one here, which we also had before. That's the same as S2, S1. Why is that? The reason is because this S1, S2, okay, I'll explain why that. So the reason is because this thing here is also the same as using the braid relation on this, okay? I can replace that S1, S2, S1 with S2, S1, S2. Whoop. Okay, so this is a rewrite of that using the braid relation. And now you can see that when we expand this with associativity, the S2 squareds will be an identity, and they will then disappear. So we're just going to get S2, S1. So that's why we're getting that thing that we already got before. So using the braid relation, we can pretty easily convince ourselves that the entire Weyl group is now already on the page here. Okay, so the Weyl group is, in fact, the Weyl group of A sub 2 is. Okay, it's a set. So I'm going to list all the matrices. There's one of them. It's a set, so I'm just going to put spaces because I like making spaces. And then there's S1, so yes, that's a generator. Space. S2. I'm putting spaces instead of commas because, well, actually, the group is not really naturally ordered. Okay, and then after that, maybe S1, S2. Whoop, come back in here. Oops, sorry, I have to put that in there. And then S2, S1. And finally, this S2, S1, S2. Yes, there should be spaces in here, okay. So we get 6 elements. And I'm going to actually also write this in a slightly different way, which is also quite interesting. I'm going to write it as the identity, and then S1, and then S2, okay? And then the next one was, which one? That one there was S1, S2, okay, S1, S2, but I said I'm not going to use commas, so let me get rid of those commas. Okay, we just have S1, S2, and then S2, S1, and then finally this one here. And to be honest, that one really has sort of 2 almost equivalent representations, so maybe I shouldn't emphasize one and just put both of them in there, right? So here's 1, 2, 3, 4, 5, 6 elements written out as words in the generators. And here are those elements written in terms of mutation matrices. So this group turns out to be pretty well the symmetric group, but we have to still define the symmetric group. So, and we have to also define what equality means here in this case. But in any case, this is really an indication of the interest of these groups is that we're connecting with actually this is the simplest non-abelian group. So this is a very important group, and the fact that it's appearing here as this Weyl group of A2 has important connections. Actually has important connections with particle physics, okay, as we'll eventually try to explain at some point, maybe in a different series. But yeah, so, and in fact this has important connections with particle physics, very important connection with particle physics. So this is a very important example, even though it's still a pretty low dimensional example. Okay, so I'm not going to go into detail with the rest. So here is A3. I'm just going to present them. Okay, we do the same kind of thing. Here's the A3 adjacency matrix. Here's the A3 adjacency matrix. Here are the corresponding mutation matrices, S1, S2, S3, obtained from the identity matrix by replacing one of the columns with the corresponding column over here and adjusting the diagonal element to be a -1. And we can check that the effect of these 3 things on a population vector is what we expect. It looks like a real mutation. Okay, when we go to Dn, well, it's good to do the D4 things first. So let's put them all in a line so you can see them here. So here are the 4 mutation matrices for the generators for D4. And here is just a check that, yes, we do get mutations. And for more general D, like D5, there's the adjacency matrix. And here are the various mutation matrices. How about E6? There's E6. There's its adjacency matrix. So it doesn't take like more than a few minutes to go from this adjacency matrix to writing these things down. And once we have these things down, well, then we have the generators of the group. Right? So if I then created products of these things, so let's, for example, suppose I define this thing here, I define this, I define this, define this and this and this. All right. So now I can do things like, S1, S2. What's that? That thing there. I can get fancier. I can do something maybe like S1, S2, S4, S1, S2. So this is the effect of doing these mutations in that order. Okay, and this is an element of the Weyl group for E6, which we saw had something like roughly 51,000 elements. And you could get all 51,000 elements by getting your computer to just take all possible products of these things until you've got sort of all of them. At some point, then they start repeating. But exactly how that works is still a subtle business that we're going to have to explore more later. Okay, and then there's E7. Okay, and what do we see for E7? There's the adjacency matrix, and here's S0, S1, S2, S3, S4, S5, and S6. Any one of these is pretty manageable, right? It's more or less just an identity matrix, except for one column where things are being adjusted in a very predictable way, actually, right? Okay, and then E8, the biggest and most interesting one, has our 8 generators, S0 up to S7. So, if you put these things into your computer, you could then try to get, to verify that you've got 696,729,600 possible 8x8 matrices that you can generate using these 8 matrices as generators. So you're allowed to take any products of these matrices as you want, and altogether, then you could end up with this remarkable Weyl group for E8. So these are really exceptional things. They're full of interest. They're full of importance for physics and for mathematics. And to start, making some headway into understanding them, we have to start with the AN case. Okay, so we have to talk a little bit about the symmetric group and how it connects with these Weyl groups for the ANs.